So now we are going to connect our binomial expansion from grade 12 to binomial distributions and probabilities in the IB course. There is a special type of distribution where an experiment has only two outcomes, and those two outcomes can't happen at the same time. It's very hard to flip a coin and get heads and tails at the same time. It's very hard. Right? They'd be mutually exclusive. You cannot get them at the same time. Okay? When this has happened, we call these binomial distributions. Even fancy name if you want to name it after some mathematician called Bernoulli. You're like, ooh, we're doing Bernoulli trials. So how do we know we have a binomial experiment? You try something a certain amount of times. You flip a coin 8 times. So it has a certain amount of times that you've done it. On each of them, there are only 2 possible outcomes. Each trial is identical and independent. So flipping the coin does not affect flipping the coin the next time. So the events are independent. Probabilities then would always stay the same. Flipping heads and tails, it's always 50%. Rolling a dice, right? We had, still up there, we had getting the 1, right? Very exciting. Not getting the 1 was 1 out of 6, that would be your success. Failure would be 5 out of 6. So notation-wise, and I'm going to change this slightly to have your new notation in there. We have the new combinations formula. And what we need to recognize here is that this is very similar, right? I'll write it out from grade 11. That's our formula for any term in a binomial expansion. Well, in a probability distribution, the probability that x equals something is identical to that formula. But instead of so what does this mean we can do? Like, we'll do a really simple one. A simple one would be flipping, one that we've done already. Flipping a coin 3 times. And let x equal the event that heads has occurred. In our probability distribution chart that we've done so far, we would have had x being heads flipped 3 times. Does it make sense that you could either get 0, 1, 2, or 3 heads? That's what we did before. And we figured out the probability x equals x from our tree diagram. We figured out that this was 1/8, 3/8, 3/8, and 1/8. But what this formula is telling us is that we could figure out, for example, this one right here using the formula. The probability that you would get 1 heads would be 3 choose 1, right? Because you're getting 1 head. So R would be 1. 3 choose 1. The probability of getting heads is 1/2. So the success is 1/2 to the 3 minus 1. And failure, or not getting ahead, would be tails 1/2 to the 1. If we multiply this out, we have 3. This would be 1/4. This would be 1/2. And we get 3/8, the same as we got when we figured it out with a tree diagram before. Okay? But what this would allow us to do is, if you had a coin that was somewhat weighted, that it was actually 75% heads and 25% tails. I don't know how you would design that. It'd be like rounded on one side, so when it flipped up in the air, it was more likely to land on the flat side. Maybe you could make a 75-25 coin. We could do this where a tree diagram wouldn't work as well. Okay? One of the things that I find really helpful, though, is to always think about this distribution chart as you're solving these questions. So notation-wise, here we have a probability function. The B means that it's binomial. The 6 says that you do 6 trials, and the 0.4 says the probability of success would be 0.4. Well, it says that in the next line too. Perfect. How would you calculate each and every event? Well, and again, I'll change this to our new notation. Six choose R, 0.4 to the R, and 0.6 to the 6 minus R. And if you wanted to find one in particular, you could just plug it into the formula. Problem with having formulas memorized is I never remember if they're in your formula book or not, but I believe this is. So let's just double check if our distribution formula is in our formula book under statistics and probability. What if it is not? And sometimes it's not, because you do have your binomial distribution. Looks like theorem, they don't give you this formula for binomial distributions. Maybe because they think it's redundant. And also because these are calculator questions, and we're going to find out that we can do binomial distributions quickly on our calculator. So if you take out your graphing calculator, and above the program button. No, above the vars button. Above the vars button it says distrib, which is short for distributions. If you go second, distrib. And hidden at the bottom is binom PDF and binom CDF. So we're going to use the binom PDF. One of them is a probability, a specific probability. The C stands for cumulative, where it adds things up. So if we go to binomial PDF and push enter, it asks you how many trials. So if we did the question, if we do this question that was just there, okay, 5 trials, probability of success 0.6. 5 trials, probability of success 0.6. Which one in particular do you want to find? When it was number 4, and you go paste. For those of you that don't have the TI-84, you have to write it out 5, comma, 0.6, comma, 4. So if you have an older version, that's what you're going to have to do. Push enter, and you get the 0.259, just like we found before. Okay? If you went, I'm going to go back to that binomial distribution, binomial PDF. If you don't put in the x value and leave that blank, it will actually calculate the whole probability chart. Like in this question with 5 trials, can you see that you would either have 0 successes, 1, 2, 3, 4, 5? You'd have 6 possibilities in your probability distribution chart going from 0 to 5. And this calculates each of those probabilities. Something that I also find very helpful on the calculator is if you hit your math button, you can change them to fractions. And it has each of them as a fraction. So you can quickly make your probability distribution chart. So just to show you that it works, using an example that we did. Tossing the coin 3 times. So I'm going to go to my distribution, binomial distribution, 3 trials, chances of getting heads, 0.5, nothing in for the x value, hit paste. We already know that the numbers were 1/8, 3/8, 3/8, 1/8. I'm going to take those, change them to a fraction, 1/8, 3/8, 3/8, 1. So you can see this thing that's built into your calculator calculates all of those things very quick. So again, one of the things that the IB program does is it says, you have technology. We live in a world that has technology. You have to know a lot of mathematics and how it works. But if we have something that calculates it for us quickly, why wouldn't we use that so that we can get further along faster, be more efficient that way? So in these calculator questions, now that you know this, it wouldn't make sense to draw tree diagrams to know how to do that. The IB would say, I want you to still know that you could do that and understand how it works. And they design questions to make sure that you understand how that works. But when you have an opportunity to use technology to make it go faster, why don't we do that? So a manufacturer finds that 30% of items produced from one of the assembly lines are defective. During a floor inspection, the manufacturer selects 6 items from assembly line. Find the probability that the manufacturer finds 2 that are defective. So how do we notice, or how do we recognize that this question is a binomial distribution question? We need a certain number of trials. They've done it 6 times. You need a probability that stays the same, and this question says it's 30% are defective. Okay? So if you wanted to find 2 defective, we could go to our calculator. We want to find the probability that x is 2. Probability of success is 0.3. This is using the formula. Okay? Put in the new notation. You could find this using the formula. You could also find this with your calculator by using the Binomial PDF. Speed-wise, probably the Binomial PDF is quicker. Right? The nice thing about the Binomial PDF, you could get your answer as a fraction. If I did the Binomial PDF and didn't put in exactly 2. So number of trials, 6 are chosen. Probability of getting a defective 1.3. I don't choose. I list them all, change them to fractions. Oh, it wasn't happy. It didn't like the fractions. What happened here is there was too many decimal places to change to a fraction, and the calculator got tired of trying, so it was like the denominators are too big. Okay? By the way, how big would the denominators be? If you made this 3/10 and this 7/10, you square that, you'd have 100 on the bottom. With 4 over here, you'd have 100,000, or no, 10,000. 10,000 times 100 would be like that's a big denominator. So I don't blame my calculator for being not very happy. Now, what do you do on a calculator when you're like, oh, I wanted to see, this is our number, right? The third one, because this would be 0, this would be 1, this would be 2. But if you wanted to see 3, you would have to use your arrow key to go over to see the rest of them. Oh, but we can answer some of the questions that we had early on in this unit that I asked, which you have no recollection of, but maybe when I ask them again. Like, remember when I said, if you flipped a coin 10 times, what are your chances of getting exactly 5 heads? That should be the most likely because of the 50-50, but it's not a 50% chance. We can now do that question. We can get our answer quickly by doing Binomial PDF 10 times, 0.5%. I'll leave them all in there. Paste. Enter. Math. Hopefully this one changes to fractions. Yes, it does. 0 times, 1 time, 2 times, 3 times, 4 times. 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads. 63 out of 256. Just a little bit less than 25%. Even though that's the most likely, it's still not very likely. And because, I mean, I always monetize these things to make money off your friends. Not a good idea. But what this means, if it's just a little bit less than 25%, if you play with someone, you could say, tell you what, if we get exactly 5 heads, I'll give you $3. If it's not exactly 5 heads, you give me $1. It's basically fair. That would be basically a fair game, because it is about 25% chance, but a little bit less than 25% chance that they win. So if you played long enough, right, if you played for like 3 days, you might be up $1.50. No. Now, sometimes they'll say at least 2 defectives. So that would mean you could have 2 defective, 3 defective, 4 defective, 5 defective, or 6 defective. So you could do this as cases and find each of those probabilities and add them up. In other words, we could go back to our binomial PDF, right? Go back to my binomial PDF. I already know that it doesn't change to a fraction. 6 trials, 0.3 of success. Push enter. Push enter. And I could add up, so it says at least 2 defective. So that would include the 0.324. Then you would have to add up 0.185 plus 0.595 plus 0.010 plus 7.29 times, do you know what this e to the minus 4 is? That's scientific notation, that's 10 to the negative 4. So you could add up those cases, 2, 3, 4, 5, and 6, 5 different cases, and get the answer. Or the other option would be, to know that all of these add up to 1. Probability distribution always adds up to 1. So my other option would be just say, well, if they all add up to 1, instead of adding up the last 5, I could just do 1 minus the first 2. That would work as well. So I think that's what I've shown here, is that it would be quicker to take the first 2 and subtract them from 1. Option 2 would be to add up. I'll write it in black. The other option would be to add them all up separately, right? X equals 2 plus X equals 3 plus X equals 4 plus X equals 5 plus X equals 6. Mathematically subtracting is a less work. And then this introduces on your calculator the letter C. Your calculator has also built into it adding them up. So we've got our answers from our calculator there with Binomipedia. Watch what happens when I do Binomipedia.
Lieutenant Ross,
Hello?
would you please dismiss a nook for the day?
Sure.
Thank you.
So that was enjoyable? No. Okay. It'd be very cool if your last name was Shook. All right, let's see then. Yeah. So if I do binomial CDF, 6 trials, 0.3, and paste it. Notice the first ones are going to be the same. My second one of my CDF is my first one and second one added. 0.42 is what you would get if you added the first 2. My third one, the 0.74, maybe you can see if you added the first 3 up, you would get that 0.74. So the binomial CDF is helpful for questions like this because if you wanted to subtract the first 2, you just have to do 1 minus those first 2. And why is this one a 1 if you're subtracting the first 2? Because in your probability distribution, the first one is a 0, then the second one is a 1. So if you're subtracting the first 2, that would be a 1. Again, in my head, every time I'm thinking about these questions, I'm thinking about, right? I'm always imagining drawing this out. X probability, X equals X, 0, 1, dot, dot, dot. I'm imagining that. And that will really help you understand these questions. The hard part for these questions is recognizing them. So if we look back at the beginning, it's a binomial distribution if you have the same percentage happen all the time and a certain number of times that it happens. This time they pulled 6 items, so we had 6 trials. Each of those trials had a 30% chance of being it. So here's the instructions in your calculator. We've done this already. How to find the Binomipedia. Oh, this would be, I believe, the exact one. So binomial CDF of 3.52 finds the cumulative probability of 0 heads, 1 heads, and 2 heads if you toss it 3 times. And it's very helpful whenever you want to find probabilities greater than or equal to something. Right? And again, this is how I would think about it. Let's say I toss a coin 8 times. You would start at 0, dot, 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 all the way get up to 8. And you want to find out, what are the chances I get more than 5 heads? So I would want to find those 3 added up. If the question said, what is the probability that you get more than 5 heads? Well, that would be getting 6 heads, 7 heads, or 8 heads. So I could just add those up, or I could do 1 minus binomial CDF, right? Because the whole thing adds up to 1. I would have to subtract all of them up to 5. So inside my brackets, I'll change it to blue. We had 8 tries. Probability of success was 0.5. And we're subtracting all the ones up to and including 5. So we would add up to 5. Then what we would be left with is the 6, the 7, and the 8 added together. But if you just look at these formulas with binomial CDF, it's like, what just happened? It's very confusing when you're looking at the formula. When you see it in a distribution chart, I feel like you can really understand where it's coming from. And everything in binomial distributions is based on that distribution chart. Sophie had 10 pots, labeled 1 to 10. Each pot and its contents is identical in every way. Puts a seed in every pot. And the seeds have a germination probability of 80%. Is it possible that all the plants grow? Yes. Is it possible that none of them grow? Yes. How likely are those things? Right? So if she planted them and she saw that all 10 of them grew, that's a good thing. But how lucky was she? Super lucky? Or does this happen to a lot of people? Right? And you always have that, right? It's like, oh, you got your assignment back. And you're so excited. You got 9.5 out of 10. Right? How do you feel when you find out the rest of the class got 10 out of 10? Because 95% is a good mark, right? But if you got 9.5 out of 10, and you find out everybody else got 10 out of 10, that 95%, does it still feel good? Or not as good as before, right? It's like, why am I the only one who lost a half a mark, right? Same thing happens sometimes, like physics seems to be a good example. You do your physics test. You got 52%. You're not feeling very good, right? Class average was 3%. Oh. All of a sudden, you're feeling pretty good about yourself. So here it is. All the seeds will germinate. Should she feel like, wow, this was crazy lucky that this happened, or is this kind of okay? Well, what do? We have 10 trials. Probability of success is 0.8. If we were using the binomial PDF, we could find out, if we put 10 in here, it finds out the specific one, exactly when it's 10. If you leave that blank, it would find out all 11 of them from 0 to 10 in your distribution chart. 10%, right? So in a classroom of 30, if all the students in biology had 10 pots and planted 10 seeds, you would expect about 3 people in class to have full plants growing. That's what you would expect. Not for sure that that will happen, but that would be the expectation. So fairly rare, right? She should feel pretty good about this. Okay? Meanwhile, next to her is Ian. And poor Ian, only 3 of his seeds grew. Oh, 3 will not germinate. Sorry, I read it wrong. So, what is the probability? So he had 7. Is that super unlucky, or is that pretty likely as well? So again, we have to read the question carefully. I did a good job demonstrating that when I read it wrong to begin with. And here, only 3 will not germinate means that 7 will germinate. And so Ian having seven plants in his pot, pretty likely, 20% more likely than having all of them. So you would have, in that class of 30, chances are there would be 6 people who have 7 of their seeds grown. What is the probability that more than 8? Okay. Again, in our distribution chart, this is what, for these ones, this is how I like to imagine it. We've got x and probability x equals x. We'd have 10 over here, 0 over here, 9 and 8. That more than 8 would be just those 2. Probability of 9 and probability of 10. Does that make sense? So you could use the binom CDF, and this part right here, 0 to 8 would get subtracted from 1, then you'd be left with the red. Or you could have just added up the 2 that were 9 and 10 separately, and you would get exactly the same answer. Okay? I think in this situation, they seem to be about equally as much work. But drawing your little probability distribution, even just without numbers like this, and circling what you have to figure out, really gives you a hint for what kind of formulas you should use. And I think it helps you understand it a little bit better as you go along. Very good?
No.
No? Of course not. Good? Okay. So if you want to look at some questions in your textbook, there's some listed. Gotcha. Good. I'll just make this, yep, I'll keep this as one video here. The average of a binomial distribution. So what can you expect if you do a binomial distribution? Is pretty easy, okay? Like if I flipped a coin 10 times, how many heads should I expect? The average is 5 out of 10. In our distribution, that had the highest percentage. Do you notice that there was symmetry when we did, like it had Pascal's triangle, so what's on the right side is on the left side, and it balances each other out. So the average of a binomial distribution is a really simple formula. It's just, how many trials did you do? What is your probability of success? I think we're going to do this, not today, but we are going to do this in this class. And I'm going to introduce it in a nice way. I just thought about introducing it in a not nice way. I was going to say that I'm not sure, maybe next class, maybe the class after, this would be the not nice way. we're going to have a test on probability. Come prepared. That would be the not nice way. We are going to have a test. And some of you will have a harder test than others. Also seems not very fun. Right? This test will be worth no marks. All the test will be to see how good you are at guessing. Some of you will have a multiple choice question test of, I have to check, I don't remember the numbers. Some of you will do 30 questions. Some of you will do 20 questions. All you get is the bubble sheet, you don't get the questions. I wish you good luck. The ones that have 30 questions, and again, I can't remember exactly, gotta find my answer, please. The ones that have 30 questions, yours are all A, B, or C. The ones that have 20 questions, yours are A, B, C, and D. Right? And then I'll put your grades into Power School after you've guessed, and everybody will be happy to see their marks. Obviously, they'll go up, right? Now, we can already figure out that on the 30-question test, you have 3 choices. What are your chances of getting it right? Theoretically, 1 out of 3. So, on average, that group should get 10 out of 30. And that 33% hopefully will boost your mark right before report cards come up. And then, the side of the class that I really need to work with. They did much worse than like the smart side, because what your chances of getting it right are 1 in 4. So on average, on a 20-question quiz, average should be 5 out of 20. 5 right, which is 25%. And I'd be like, how come these guys are smarter than me? We'd be like, well, it's not fair. Okay? And then we'll also be able to find out, like, there might be some really good guessers in class. And there might be some really bad guessers in class. Oh, I got a story. Oh, I have 2 stories about bad guessing. One of them I've completely forgotten, but it's the better story. I'm going to see if I can remember it. The story, oh yeah, I do remember. Okay. But I'll tell you the not quite as good story first. So the not quite as good story in guessing was one time I had a grade 10 class, and it was the beginning of the month, just like today, new seating time. But instead of doing it randomly, I said, I'm going to let you choose. The spots are up there. But in order to get a chance of choosing, you have to guess what I rolled. So I'd roll the dice. I'd say, yeah, we'll start. Well, no, Yihong, you guess first. I rolled, what do you think I got? I rolled the dice. What number? 3. No, it's not 3. No. What? No. No.
6.
No.
5.
Good. Okay? You would hope she would get that right. I did roll a 5. Okay? So then, Alexis would pick first, pick whatever spot, and then we would start again with Jessica and go through. Now, the boy that sat right here guessed wrong on the first try. When it came around to him every single time, he guessed wrong. He even once guessed wrong when all the numbers had been chosen and only one number was left. He wasn't paying attention and guessed wrong. Finally, he was the last one left, and there was one spot on the board. But I said, no, you don't get that spot unless you guess the number correct. And I rolled the dice, and he got it on the 6th try. That was a great example of bad guessing abilities. Okay? The other crazy story. Yeah, I was a little bit. I had a deck of cards. So I pulled the card out and I put it down. And I gave. It's like, can you guess the card? And student, and then I went through the deck. I noticed there was only 3/4. So I took 3/4 out and I passed them to another student who saw the 3/4 and that the 4 parts was missing. So I went to the student. I said, what part do you think this is? They said, I think it's a 4. And the student went, because they were excited. Because the 4 seemed to be right. And then they were like, well, what suit do you think it is? And they said hearts. And this one's like, oh my goodness, because there was 3/4 and the 4 parts. Wasn't there? Flip over the card. Queen of Spades. Total disappointment. We looked through the deck. The deck had 51 cards. There was 1 card missing. It was the 4 of hearts. It was the only card possible to pick that had no possible chance of being right. And the student picked it. Which was pretty funny. A pretty good story. Okay, so our mean formula is a super easy formula. It's just however many trials times your probability of success. So if I give you 100 multiple choice questions and you have a 1 in 5, so it does like biology does like 5 options. They have like 8 options. Right? If it was 1 in 5, then on average you should get 20%. We can also find, and now we start to connect to our statistics unit, we can also find the variance of our binomial distribution. And it is also a kind of really simple formula. You just take your probability of success, your probability of failure, and the number of trials. So if we did 100 multiple choice questions with a 20% chance of getting them right, an 80% chance of getting them wrong, this would tell us that our variance would be 16, which we could then take the square root of and find out that our standard deviation would be 4. Now I'm going to see. Make sure that under statistics I'm not lying. Yes, this is on, oh, even the mean formula is on there for binomial distribution. Perfect. But standard deviation, square rooting it, you'd have to remember that from your statistics unit. And this is where things start to get a little bit crazy and a little bit exciting. We start to recognize, so on this 100 multiple choice question test, possibilities in our binomial distribution, right? If you guessed on 100 multiple choice questions and you got 100%, like, insane. It's possible, but that would be insane. Most people are going to get 20 with a standard deviation of 4. So if I go up by 4s, try to scale this correctly, 24, 28, 32, and I go down by 4s, 16, 12, I don't know if my scale is so big, okay? We are going to find that combination of probability and statistics will tell us that the data will end up looking like this. And between 3 standard deviations above and below will account for 99.7% of all people. So if you had 100 people do this multiple choice question quiz, you could say, very, very unlikely anyone would get above 32 or below 8. Because 99.7% of 100 is like almost everybody is going to get from 3 below to 3 above. 2 below to 2 above. Will be 95% of people. So very few people will get between 28 and 32 and between 8 and 12. But there will be some. 100 people wrote it, about 5% would be split up between the super good guessers and the super bad guessers. And one standard deviation above and below is roughly 68%. And this is so important that they even made a rule to help you remember this. Okay? Does anybody know what the rule is called? It is called the 68, 95, 99.7 rule. It's a great rule, eh? At least it helps you. I mean, if they gave you some like the Bernoulli rule, you'd be like, never remember it. But the 68, 95, 99.7 rule really helps you remember it. That within one standard deviation, 68% of data will happen. And within 2 standard deviations, 95%. And 3 standard deviations, 97%. And this curve, have you heard of the bell curve? This curve looks like a bell. And they call it the bell curve. Like, whoever is like probability statistics people, they're good, right? They come up with names that really can help you remember stuff. So there we have the bell curve. And this is used sometimes even in your IB marks. IB marks are like, most of people should be in here. Most of people, so this is like your 4s and 5s. And then, or maybe 3 4s and 5s. Let's have 68% of people get 3, 4, and 5. We're only going to let a few people go into the 2s and the 6s. And a few less people into the 1s and the 7s. And so when you mark on a curve, I had a statistics professor once who found out that he was in first year university, and his teacher said, I mark on a curve like this. So most of you, the average is going to be 75. The very best student is going to get 100. The very worst student is going to get 50. This is my statistics professor. Okay? He ended up being a professor, so he was smart, but he made a bad decision that year. He was like, I can do nothing and get a 50. Yes, the lowest. Professor said the lowest. So he didn't go to any of his classes. It's kind of funny, he became a statistics professor after. Realized he didn't learn anything his whole first year of statistics, but he got a 50 and he got the credit. Not necessarily a good choice. Right? I, on the other hand, would have been smart and convinced everybody, hey, you guys realize that if you do nothing, you still pass? And then I just do one assignment. And I would get the 100 for being the top in the class, only doing one assignment, and everybody else would get the 50. There probably someone who would do 2 assignments. Okay. Ooh, unearned question. What do you think? We have time to at least start it and think about it. An urn contains 7 marbles, of which 2 are blue. A marble is selected, its color noted, and put back in. You do this 50 times. You're having a great day. Find the probability that you selected 10 blue marbles. So how do we recognize this as a binomial distribution? We have a certain number of trials. We've done this 50 times. The probability stays the same the whole time because the marble is put back in. Your chances of getting a blue marble are 2 out of 7. So what can we do to figure this out? 50 trials, probability 2 sevens. Go to Binom PDF. 50 trials, 2 sevens. We want to find exactly 10, 5% chance. Or if you wanted to, you could use your binomial theorem formula. I know you probably don't care, but why the binomial theorem works here is because if you had this to the exponent of 50, first of all, mathematically, I hope you can see the answer is 1, right? To find out the answer is 1 to this, you have 2 options. You could add the inside, find it's 1, and 1 to the 50 is 1. Or you could use your binomial theorem and write out all 51 terms, then add them up, and find out your answer is 1. So just quickly to end here, what we're doing when we do the 50 choose 10 is imagining that you have all 50 of them. And when you multiply them all together, each term is a different combination of picking a 2 sevens or a 5 sevens. And the 50 choose 10 gives you all the ways of choosing exactly 10 of the 2 sevens and 40 of the 5 sevens, depending on where they are in that. And so that's the connection between the binomial expansion and why that formula works.